Welcome to the course module of Communication Engineering. So here we are today on our 14th lecture. So in the last lecture, we have already seen the generation of the Ssbc signal by using the frequency discrimination method and phase discrimination method. So now today I'm going to talk about two different topics in which first of all I will be talking about the quadrature amplitude modulation, and later on I will be discussing about the a brief discussion I will be doing on the vestigial sideband modulation. So let's see from this scheme of phase discrimination method of generation of the Ssbc signal. I told you that in this scheme, what we need to do is we have to take the message signal, and then we have to take the Hilbert transform of this particular message signal, and then this particular scheme we have to take, in which we have to take the carrier signal, and then we have to take a quadrature carrier. Then by following this particular scheme, we have to generate a Ssbc modulated signal. That will be depending on plus and minus sign, whether it is upper sideband modulated or lower sideband modulated. That we have already seen in the last lecture. Now today, just I'm modifying this scheme a little bit. Okay, the modification is only regarding with the taking messages signals. Okay, I will be taking this block diagram as it is. Okay, whatever we have taken in this case of generation of the Ssbc signal. But the only difference is that what we have to take is we have to take two different message signals. Okay, and that message signal need not be in quadrature in phase. Okay, so how to utilize that particular thing to save the bandwidth, that we have to look at, and that discussion is our regarding the quadrature amplitude modulation. So let's see this how this phase discrimination method can also be used for as a bandwidth saving scheme, and this can also be used for sending two DSBAC signals in the same bandwidth. DSBAC signal is taking bandwidth equals to 2W or 2FM. Okay, within the same bandwidth we can send the two DSBAC signal, and thereby we can save our transmission bandwidth. So let's see what is the quadrature carrier multiplexing or quadrature amplitude modulation. Okay, so normally this scheme is called either quadrature carrier multiplexing or quadrature amplitude modulation, or simply quadrature modulation. So you see, if you compare it from the previous diagram, what I have taken is this particular section is remain same. Okay, this particular section is remain same. The only difference that you can observe here in this diagram is I have taken in the upper arm, I have taken one message signal which is M1T and another message signal which is M2T. Okay, so now when we have this two message signal, and then if we are using a carrier AC cos omega CT, I can take a quadrature carrier. Okay, that will be our AC sin omega CT. Now I can multiply it separately to the separate message signal like at M1T and M2T. And then we can add these two signals. Okay, so once we will adding these two signals, this signal will be our ST. Okay, and that ST you can see here, it will be given mathematically as M1T AC cos 2 pi FCT plus M2T sin 2 pi FCT. Now if our message signal M1T and M2T both are two different message signal but occupying the same bandwidth 2W, then what happens is within this bandwidth of 2W, both the message signals can be transmitted. Okay, so without disturbing each other, these two message signals M1T and M2T can be transmitted. Okay, and therefore we can save our transmission bandwidth. Okay, so how to demodulate this message signal, whatever we have done in our previous lectures, by following the same method again, we can go for the synchronous demodulation of this particular modulated signal. So what we have to perform is, once our message signal, once our modulated signal ST will be received by the receiver, then again we have to multiply with the same carrier. For example, in the upper arm, what we can say is the demodulation scheme is our synchronous demodulation, in which I am multiplying here is 2 cos omega CT. Okay, as the carrier. The another carrier is our 2 sin omega CT. Okay, so if we multiply 2 cos omega CT, then obviously if you multiply in this particular equation 2 cos omega ct, you will be able to separate out m1t, and m2t will be completely lost. As we know that in the case of quadrature null effect, if you remember, I have already explained it. Whenever we multiply a carrier which is with quadrature in phase, okay, at the receiver end, then that message is completely lost. So here you can see that in this case, we are having m1t is multiplied with the carrier cos 2 pi fct, and m2t is multiplied with the sin 2 pi fct. So obviously, when we multiply a message, this particular signal, modulated signal, quadrature amplitude modulated signal, ST, with this particular carrier 2 cos omega ct, then this component will be completely lost. Okay, so m2t will be completely lost, and we will be left with the message signal m1t. So it is very simply, we can have a low pass filter, and the output of the low pass filter will be m1t or proportional to m1t. That can easily be shown, okay, by just taking this 2 cos omega ct and multiplying to this particular equation. Similarly, if you want to extract m2t, then we have to multiply sine omega ct. You do not bother about this factor 2 or 2, okay? You can take it 1, 2, 3, whatever, okay? But if you are taking 2, then obviously you will be getting some simplified equations, okay? That will be m1t and m2t. So you can just do it, okay? You will be able to observe that the output will be proportional to m1t in the upper arm and the m2t in the lower arm. Okay, so this way we will be able to separate out this two messages signals m1t and m2t by multiplying an appropriate carrier at the receiver side. So basically what we are saying, that it is possible to send two DSBC signal, because if you see separately, this m1t multiplied with the carrier is nothing but our DSBC signal. Okay, we have already seen what is the equation for the DSBC signal, so it will be representing our DSBC signal. Similarly, the second factor m2t sine 2 pi fct, again it is denoting you a second carrier. Okay, so please, you do not here I have not written like AC sine 2 pi fct. You can write here AC 2 pi sine ft, okay, 2 pi fct. It will be results you again in the same output. Okay, you just take care of that. I have not written here it is AC sine 2 pi fct. Again, it is not written here in the diagram also, but we can write here AC 2 pi fct. Okay, so obviously these two DSBC signals we are sending together, okay, by just multiplying two quadrature carriers, and these two quadrature carriers is actually used for demodulating the two different messages signals separately at the receiver end. So within the 2W bandwidth, we are able to send two DSBC signals, and thereby what we are saying, that we are able to conserve the bandwidth. Okay, we are able to conserve the bandwidth. Now, one more observation that we have to take care is while multiplying this carrier at the receiver side, okay, as we have taken in this last case, what I am saying is, if this carrier that we are using is perfectly synchronized with the carrier that we have used at the transmitter side, okay, that means it is having the same frequency and the phase, okay. So if this is the case, then obviously we will be able to get the m1t and m2t separately. But what happens if it is not perfectly synchronized with the carrier at the transmitter side? And let us suppose that there is a frequency offset, means the frequency is not same as that we have used at the receiver end, transmitter end, sorry. So let us suppose that if we are having a carrier, for example, 2 cos 2 pi fc plus delta ft plus phi. Okay, if instead of multiplying 2 cos omega ct, if we multiply this particular carrier 2 cos cos 2 fc plus delta ft plus phi, in which delta f denotes the frequency offset. Okay, it may be plus delta f or it may be a minus delta f. Okay, so it means that the frequency is not same as fc, but it is a little bit deviation in the frequency fc is observed. Okay, and similarly, it is not having the same phase, but it is having a certain phase offset. Okay, so again, we can take this carrier. Okay, if you take this carrier and if you multiply with this particular equation of st, then it can be shown that in the output of the upper branch, okay, means after low pass filter, okay, after passing through the low pass filter, we will be able to show that the output will be something like this. Okay, So I request all the viewers, please follow my all previous lectures, okay, because it is very easy and very simple to demonstrate this equation. Okay, it is not very difficult to show this equation. So please try to work out this one. You will be able to show that if we are taking this carrier 2 cos 2 pi fc plus delta ft plus phi instead of 2 cos omega ct, then after multiplying with this equation st, we will be able to show that the output of the upper branch would be this one, okay, which is nothing but our AC. Then in this bracket, m1t cos 2 pi delta ft plus phi, and then m2t sin 2 pi delta ft plus phi. So this will be our equation, okay. Similarly, if you multiply in the lower branch, okay, if you multiply 2 sin 2 pi fc plus delta ft plus phi, in that case the output will be this, okay, output will be this in the lower branch, okay. So this will be the output after the low pass filter. Now if you observe this output, okay, I hope you will be able to do the calculation and you will be able to get this output, okay. So once you will be able to get this output, now what observation we have to make from this equation is, here you can see that this m1t is actually being multiplied with the cos 2 pi delta ft plus phi, and m2t is multiplied with sine 2 pi delta ft plus phi. So what we need to understand from this equation is, if delta f, suppose that if we are taking the cases like if delta f and phi is equals to 0, in which we are saying that the carrier that we are using at the receiver end is perfectly synchronized with the carrier at the transmitter end, then that case delta f and phi will be equals to 0. So if you substitute delta f and phi equals to 0, then what you will be getting, m1t is multiplied with the cos 0 minus m2t will be multiplied with the sine 0. And as we know that sine 0 will be equals to 0 and cos 0 will be equals to 1, then in that case we are again going to get output which is proportional to m1t, okay, that we are supposed to get. Okay, here you can see in this particular block diagram that in the upper arm our output should be proportional to m1t, okay. So our output is proportional to m1t when it is perfectly synchronized with the carrier at the transmitter end, and delta f and phi equals to 0, okay. Similarly, if you see in the output at the lower branch, if delta f and phi equals to 0, again what will happen here, it is m2t is multiplied, okay. So this will be equals to cos 0 will be equals to 1, okay. So this output will be proportional to m2t, and this m1t will be completely lost, okay, because it will become sine 0, and because of sine 0 it will be completely lost, and we are going to get the output that will be proportional to m2t. So here we can see that obviously when our carrier at the receiver side is perfectly synchronized with the carrier at the transmitter side, then the output is proportional to m1t and m2t. But suppose if this is not the case, then what will happen? Okay, if this is not the case, either delta f is exist or phi is existing or both are existing, okay, then obviously the output will be given by this equation. It means that the output at the upper branch is not only containing the desired output m1t, but it is also containing a certain part of message m2t. Okay, it will also be containing a certain part of m2t, and that will be related by this particular equation. Okay, it means that the upper branch or the lower branch output is not as a desired output, but it is also containing the output at the its output is also containing the other message signal. Okay, it means that the other message signal is interfering with the desired message signal. Okay, and generally when this happens, because where you can see that m1t and m2t both are present, again in this output of the lower branch, m2t and m1t is both are present, and therefore this particular problem is called as the co-channel interference. Okay, you remember that whenever there is a phase offset or a frequency of offset is existing in the quadrature carrier multiplexing scheme, then there is a chances of co-channel interference in which both the signals m1t and m2t will be interfering each other. Okay, so this is our co-channel interference. Okay, co-channel interference. So remember that this quadrature carrier multiplexing is used for saving the transmission bandwidth. Okay, in which we are using the quadrature carrier, and we are using the two different message signals, and both the message signals will be Dsbc modulated, and it will be sent within the same bandwidth. and it will be able to use the it will be able to use the same bandwidth, and therefore we will be able to save the total bandwidth requirement for sending the message signal. Normally, the QAM is used in the TV signals, okay, in which we are using the chrominance signal of the TV to send at the receiver end. Okay, so chrominance signal is nothing but the color information of the television signals. So that basically used transmitted by using the QAM method, Quadrature Amplitude Modulation scheme. So now, if you have understood, I hope you must have understood this topic, okay? What is quadrature multiplexing, okay? Quadrature carrier multiplexing. Now, today we have to look at another modulation scheme, which is our vestigial sideband modulation, okay? So let's see this, what is vestigial sideband modulation technique. So as we have already seen this previous lectures, that if we are taking a particular message signal, we have so far seen different modulation schemes. For example, the first we have discussed the conventional AM case, in which we were using, we have sent the two sidebands along with the carrier. Okay, then we have seen the double sideband modulation, modulated scheme, double sideband suppressed carrier, in which we suppressed the carrier part and we retained only the our sideband parts. Okay, then we have seen the SSB SC. Okay, in SSB SC scheme, what we do is we are suppressing one of the sideband and we are retaining only one of the sideband. For example, in this case, it is upper sideband modulated modulated scheme. Okay, so in which we are just retaining the upper sideband. Okay, and the lower sideband is actually completely eliminated. Okay, so if you see what is the necessity of moving from AM to DSB, what is the necessity from moving from DSB to SSB, and then why we are going for SSB to VSB, that is very important to understand. So if you see that, if we have seen our AM modulation case, we have said that most of the transmitted power is actually wasted in transmitting the carrier. Okay, and carrier is not containing any information. Okay, but because of carrier is giving us simplicity in demodulating the conventional AM, because we have a simple receiver like envelope detector that can be used for demodulating the conventional AM signal. We used conventional AM, but if you see, because of the wastage of the power, we removed the carrier part. Okay, and then we talked about the DSBSC signal. Okay, so in the DSBSC signal, we removed the carrier power, and therefore we will be able to we were able to save the transmitted power, total transmitted power, modulated power, and our modulation efficiency become 100%, because all the powers was actually resided in the sidebands only. Okay, but the problem was that we have seen that in the conventional AM and the DSBSC case, both is occupying the same bandwidth. Okay, it's 2W. Okay, so it was not bandwidth efficient, and therefore what we did is we further reduced one of the sideband, because we said that only one sideband is sufficient to get back the original message signal at the receiver side. And it is not only reducing one of the sideband, because of the reduction of the one of the sideband, not only bandwidth is saved, but power is also saved. Okay, that we have seen in the SSBSC case. Okay, now we have another scheme. Okay, we have another scheme. Okay, I will be tell you what is the reason why we are going for the VSBSC case later in the other lectures. Okay, but today you see, first of all, what is the difference between this SSB and the VSB scheme. Okay, so here we can see that in the SSBSC case, what we did is we completely removed one of the sideband and we retained only one sideband. Okay, by choosing an appropriate filter or by choosing a particular generation method of the SSBSC signal. In the VSBSC case, what we do is we are not completely removing the one of the sideband. But what we did is we are almost retaining one of the sideband, almost. You remember that it is not completely we are retaining the sideband, but we are almost retaining one of the sideband, and a part of the other sideband is also retained while transmitting the signal. what we are doing is in the VSB, as its name suggests, is a vestigial sideband modulation technique. Okay, so what we are doing is we are means keeping almost the wanted sideband completely. Okay, a little bit part is actually removed. Okay, here you can see in this part. Okay, a little bit part is actually removed, and then we are also keeping a little part of the other sideband. Okay, so here you can see VSB refers to the modulation schemes where in the wanted sideband is retained almost completely. Okay, it is almost completely. You remember that it is not completely we are keeping it. Okay, almost completely and completely keeping it is different. Okay, so we are removing a little part of these wanted sideband also. Okay, so a trace of the other sideband is also sent in the case of VSB signal. So basically, if you see the bandwidth requirement of the VSBSC signal, if you compare with the SSBSC case, here you can see that the bandwidth requirement is greater than the SSBSC case. Okay, and here we can see that the power requirement may be or may not be same. Okay, as the SSBSC case. Okay, so that will be a different thing, but here it is important to understand the bandwidth requirement for the VSBSC modulated signal will be more. Okay. So basically, how to generate this type of VSBSC signal that we have to look at, and what are the implications that we have to see. Okay, so basically, here you can see that the same like we have done in the case of the SBSC signal, we have to take the product modulator, we have to take the masses signal, and then should be multiplied with the particular carrier, and then this DSBSC signal will be passed through a particular sideband filter. Okay, SBF means it is a sideband filter. We have to take a vestigial sideband filter. Okay, so basically a sideband filter of a particular characteristics will be used to generate this type of VSBSC signal. So that we have to look at what should be the characteristics of the sideband filter and how this VSBSC signal can be generated. Now, one thing that is very important to understand in the case of VSBSC signal is if we are sending this type of signal, okay, if we are sending this type of signal, then how this signal would be demodulated and how will we able to get back the original masses signal when we are sending a little part of the unwanted sideband and a little part is also clipped in the case of wanted sideband. Okay, so when we are sending this type of spectrum, then how this is going to be demodulated? It is more important to understand. Okay, so to understand that, when first of all we will be trying to understand how we have demodulated a DSBSC signal or SSBSC signal. Okay, so that I will be telling you by just having the spectrum. Okay, only the spectral analysis. Okay, so you try to understand from this spectrum itself. Okay, let us suppose that we are having this type of masses signal. Okay, so if we have this masses signal whose bandwidth it is a multi-tone signal, obviously, and its frequency spectrum is ranging from 0 to FM. Okay, and it is our baseband signal. So this is our masses signal. So generally what we do is we are taking this type of masses signal, and to generate the DSBSC signal, what we do is we are multiplying an appropriate carrier. So let us suppose if we multiply an appropriate carrier FC, then what happens is this particular spectrum will be shifted around carrier frequency FC. And this type of spectrum we are going to observe. Okay, so once we are going to get this type of spectrum, here we can see that it is shifted around FC and minus FC. Okay, and then we are getting this type of spectrum. Okay, so that will be the spectrum of our DSBSC signal. So now at the demodulator end, what we do is in the case of synchronous demodulation, okay, what we do is we are actually multiplying the same carrier again. Okay, so as we can see that after multiplying this particular masses signal with the cos 2 pi FCT, this particular spectrum was shifted around the carrier FC. Similarly, now this spectrum will be acting as a message, and when we multiplied with the same carrier cos 2 pi FCT, again this spectrum is going to be shifted around our carrier frequency FC. The meaning is this is going to be shifted like F minus FC. Okay, if it is SF, then this spectrum will be something as F minus FC and plus S plus F plus FC. Okay, so that will be our spectrum, and this spectrum is going to be right shifted, and then again it will be left shifted. Okay, So in that case, what we can understand is this particular portion will be shifted right hand side, and this will be also shifted right hand side, and this portion will be coming around 0, okay, because it is shifted by a frequency fc. Similarly, it will be again right shifted and left shifted both, okay. So when it is left shifted, it will be going towards this side. So what happens is this, because of this shift, okay, what happens is this portion is going towards this side and this portion is going towards this side, and then this two will be added together to generate a massive signal. That will be our MF, okay. And then what we do is we are passing through a low pass filter, and then we are able to recover back this particular massive signal. Same thing is happens when we are talking about our SSBSC case. Okay, what happens is in the SSBSC case, first of all, we are taking the massive signal, and then after having the massive signal, we have to generate the DSBSC signal, and after that, we have to pass it through a particular means filter or a particular generation method, and then we will be able to generate a particular USBSC modulated signal. So this is our USB modulated signal. Okay. So after multiplying with the carrier, this has been shifted around FC. Okay, and one of the sideband is actually eliminated or removed. Now again, if we multiply this particular spectrum with the same carrier, okay, in the case of synchronous demodulation, then again this spectrum will be right shifted and again it will be left shifted. Okay, so because of that, again this portion is to it will be means moves towards this side. Okay, and this will be shifted means it will move towards this side, and again it will be added together to generate a massive signal. Okay, again you can see that this spectrum will be nothing but our massive signal. So basically, after passing through the low pass filter, we will be able to get back the massive signal. So you try to understand the same thing that I have shown here, okay, how we generate the SSBSC signal or we generate the DSBSC signal, okay. So basically in the SSBSC signal, what we are saying is we are taking the massive signal here, okay, and then this massive signal has to be multiplied with the particular carrier cos 2 pi FCT, and therefore this particular spectrum will be shifted around massive signal. Now, one of the sideband is eliminated here, and then again we have to multiply while doing the demodulation process. Okay, we have to multiply this particular spectrum with cos 2 pi FCT. So once we multiply, then what will happen is there will be a shift of this particular modulated signal. So that will be your SF minus FC. This is represents SF minus FC, and this represents SF plus FC. So now what happens is, because this is our higher frequency component 2FC, and we need to pass this particular signal, this two should be added together. Okay, because we know that the spectrum will be SF F minus FC plus F plus FC. Okay, so these two should be added together. So this portion and this portion will be added, and that will be able to form our massive signal. And now this 2 component minus 2FC and plus 2FC, this will be eliminated by having a low pass filter, because low pass filter will be allowed only the baseband massive signal, and this higher frequency component will be eliminated. Okay. Similarly, again we can look at if it is a VSBSC signal, then how it can be generated. Okay. So first of all, we have to take the massive signal, a DSBSC signal would be generated, and then this should be passed through an appropriate filter so that this type of spectrum would be retained. Okay, this type of spectrum would be retained. Okay, so after having this, again to demodulate this particular VSBSC signal, what we need to do, again if we are interested in the synchronous demodulation, then again we have to multiply it with the same carrier. So once we do this, if we multiply it with the same carrier, then what happens, again this spectrum will be shifted right side and the left side, and then this 2 spectrum has to be added together. So once it will be added together, here we can see that a certain portion, okay, a certain portion will be remain same, and now a certain portion of this spectrum is going to be overlapped. Okay, there is a certain portion which is going to be overlapped. Okay, if you compare it from the previous slides, okay, if you see this slide, okay, here in the case of SSBSC signal, this spectrum and this spectrum is not overlapping. Okay, but there must be an overlap in the case of DSBSC signal. And because of the overlap, the frequency spectrum will remain same, but the strength of that spectrum is going to be doubled. Okay, you remember that its strength is going to be changed, its amplitude is going to be changed, but the spectrum will remain same. Okay, you remember that. Okay, in the case of Ssbc signal, this spectrum is not overlapping, but in the case of Vsbc signal, we can see that there is a certain portion. Okay, this much amount of portion is going to overlap. Okay, so to get back this original message signal, this overlapping portion should be such that if we add them together, it will be able to construct this portion. Okay, should be able to construct this portion so that we will be able to get back the original message signal. So I hope this must be clear. What I am trying to explain is if we are going to demodulate such VSBSC modulated signal by using the coherent demodulation, okay, synchronous demodulation scheme, then a certain portion is going to be overlap, and this overlap has to be controlled in such a way that if it will be added together, then the resultant signal that we are going to get should be our message signal. Okay, it should be a message signal. Okay, so how to get that? Okay, how to get that we have to look at how to get that. Okay, so that it will be look like something we have passed the signal actually through a low pass filter, and the other high frequency component will be eliminated, and the constructed or reconstructed signal will be our message signal. Okay, so that we have to look at how this overlap should be done. Okay, so that our message signal will be our demodulated signal will be our original message signal. Okay, so that will be actually done by having a particular characteristics of the sideband filter. Okay, as I said that basically we have to generate a DSBSC signal first, and after having the DSBSC signal, it has to be passed through a particular sideband filter, and that we have to look at what should be the characteristics of the sideband filter that is going to give you that type of VSB spectrum that will be we will be able to demodulate by using coherent demodulation scheme, and the output will be our message signal. So the requirement that our message would be will be demodulated properly, okay, by coherent demodulation scheme, we need to have this type of filter characteristics. So what is the conditions? Okay, the first condition is that if we want to undistorted output, okay, at the demodulator end, what we need is our filter characteristics is something like this. Okay, if we have a filter characteristics HV, okay, suppose if it is denoted by HV, then this filter characteristics, if it is right shifted HVF minus FC, or it is left shifted HVF plus FC, then the addition of these two should be a rectangular low pass filter. Okay, its characteristics should be a rectangular low pass filter. Okay, it should not be a some other filter. Okay, if it is a rectangular low pass filter, then only this means filter will be able to generate a particular VSBSC signal that could be demodulated easy by synchronous demodulation. The other requirement for this filter is our phase characteristics of the filter should be a linear function of frequency. Okay, so first of all, you try to understand what is the phase response and how it is related, why it is important. So basically the phase response denotes you the delay produced by the circuit. You try to understand whenever we are giving a particular input to a particular system, okay, then the output generation will take a finite amount of time. Okay, so it may be like 1 second, 1 millisecond, 2 millisecond, or it may be in microseconds. Okay, so it will take a certain amount of time, and after a certain amount of time, the output is going to be produced by the circuit. So that delay is actually related to the phase response of our filters. Okay, so phase response of this filter is actually denoting you the delay. You try to understand that one. Okay, so if the phase response should be linear. Okay, should be linear function of frequency. Why it should be linear function? Because phase response or the delay produced by the circuits, okay, it will be depending on the input frequency. Okay, so for the different amount of frequencies, if the delay produced by this filter is different, then the output that we are going to get will be annoying. Okay, so if we are able to keep it a linear means frequency phase response, okay, if the phase response is linear, in that time what will happen is whatever be the frequency of the input signal, okay, all the frequency component is going to be delayed by the same amount by this particular filter. Okay, so there will be a constant phase delay. We try to understand that what is the necessity that the phase response should be a linear function. Okay, if it is not a linear function, what will happen? Okay, the thing is that if it is not a linear function, then the different frequency component is delayed by a different amount by this particular filter. Okay, if it is a linear function, then all the frequency component is going to be delayed by the same amount of time. Okay, so delaying output is not making any error. You try to understand if any output that we are going to get in a delayed time, okay, if it is 2 milliseconds delay or 5 milliseconds delay, there will be no harm in it. Okay, but if different frequency component is delayed in a different amount of time, then that output will be annoying. Okay, and that will be creating a very annoying output. Basically, if it is our video signals, okay, we are generally not able to observe the this type of phase distortion in audio signals, and it is in the most of the cases it is acceptable, but the phase delay problem or phase distortion in the video signals are not acceptable. You try to see this one. Okay, so basically what is the two requirement is that our filter that we are going to use for generating the Vsbc signal sideband filter should have a characteristics that will be following this particular condition, in which if we are shifting this to filter characteristics, okay, HVF minus FC or HVF plus FC, it is going to give you, it should give you a rectangular pass band. You remember that in this particular frequency range of our massive signal, like minus W to plus W. Okay, so within this, it should be able to give you a rectangular pass band. Okay, it is not necessarily one, it should be any constant. Okay, it should be, it can be any constant like 1, 2, 3, 4 or anything k. Okay, so that will be a rectangular pass band. Okay, similarly, the phase response should be a linear function, and then the phase response at f equals to fc. Okay, at f equals to fc, it should be given by this particular equation. Okay, it should be minus 2 pi m, where n is an integer. Now how this filter can be designed. Okay, how this filter can be designed. So here you can see that if we take this type of filter, okay, if we take this type of filter characteristics, okay, so filter can be means represented by this particular equation in its magnitude phase representation, in which we are having HVF equals to mod of HVF e to the power j theta bf. Okay, so basically this represents the frequency response in the frequency range of this, okay, from FL to FC plus W. So basically, if we take this type of frequency response, you remember that we are talking the most important part is this part. Okay, only this part is more important, but the other part is not important. Only this part is more important.